Hi, this is a video as an introduction to thermochemistry. Some of this will be review, but you're going to learn some new concepts. So first of all, there's three laws in thermodynamics, and in this video we're just going to learn the first law. And that's the law of conservation of energy. And so the first law of thermodynamics states that energy is conserved. It cannot be created or destroyed in a chemical reaction. It can be changed from one form to another, but the overall amount of energy is conserved. So what exactly is energy? Well, energy is defined as the ability to do work or to transfer heat. There are two main forms of energy. Kinetic energy, which is the energy of motion. And so we talked about kinetic energy in terms of temperature. So the higher temperature means you have a higher kinetic energy. So that means that the molecules are just moving faster. So I want you to think of kinetic energy also as temperature. And then there's potential energy, and that's the energy of position. There are two parts to energy, and that is heat and work. And as we've seen in calorimetry, heat has the abbreviation Q, and its definition is the transfer of energy due to temperature differences. Work, the abbreviation is a W, and it's a force acting over a distance. So heat and work are the two parts of energy. The units of energy, there are several different units, but the most common one is the joule. That's the SI unit, and you can add any prefix you want to that, kilojoule, millijoule, whatever works with the magnitude of number that you're working with. There's also a unit calorie, and actually the calories in food are actually kilocalories. All right, let's talk about the system and surroundings when we talk about a chemical reaction. The system is what is reacting. The surroundings is everything outside of the system, and then they use the word universe to mean the system and the surroundings. And then there are three types of systems. An open system is a system in which matter and energy can be transferred from the system to the surroundings or from the surroundings to the system. So that would be like doing a reaction in a test tube and say you generate a gas, and we've done that a lot this semester, and that gas escapes, that's matter, it escapes from the system to the surroundings. A closed system would be one where matter cannot be exchanged with the surroundings, but energy can be transferred from the system to the surroundings. So that would be something like, your test tube heats up. No matter is leaving your test tube because you put a cork in it, but the heat that is generated is being lost to the surroundings. And an isolated system means that neither matter nor energy is transferred between the system and the surroundings. So energy flow in and out of the surroundings. So here, let's go back here. In our first example, what if we add energy to a system? Well, the energy has to come from somewhere, because remember, the first law of thermodynamics says that energy is not created or destroyed. So we are taking energy from the surroundings. Okay, from the point of the view of your system, energy has been absorbed. So energy has been absorbed by the system. Okay, so our reaction is called endothermic. When you absorb energy into your system, it's called endothermic, and this is supposed to be a delta, so the Greek letter delta. Delta E for that is positive. So you're taking energy from the surroundings, and so then it's going into your system, and that's endothermic. And so the surroundings, which is what we can measure the temperature of, would be going down. Okay, what if energy is lost by the system? Well, then the energy is going to the surroundings. So our energy is going up. Oops, I'm sorry, I'm having some issues with my pen for a minute here. Okay, so if energy is lost by the system, energy is going to the surroundings. So from the point of view of our system, energy has been released. And when your system releases energy, we call that exothermic. In other words, the energy has left or exited the system. And we can measure the energy in terms of temperature in the surroundings, and delta H would be negative. Exothermic reactions, delta E is negative. Okay, so this diagram really helps me understand this. So here's our chemical reaction. So that is our system. This is the surroundings, everything, outside of that little box. And then both the system and the surroundings would be called the universe. Okay, so if we have heat that goes into our system, so like here, so heat's going in, okay, that is endothermic, okay, and the delta E of the reaction is positive. And then if energy is released from the system, then the heat flows out of the system, and it's called exothermic, and the delta E is negative. All right, now this is a review for us, but it's something very important. Remember our reaction profile. So here we've got, this is energy here, and this is our reaction pathway. And what's important about an exothermic reaction is that where you start, the energy is higher than where you end. And now remember, delta is always final minus initial. So this number, which is smaller, minus that bigger number in energy, which is, so a smaller energy minus a bigger energy gives us a delta E that is negative. And that's what we said. Exothermic reactions have a negative delta E. It has released energy to the environment. Well, in contrast, we have our endothermic reaction. Let's see here. And what is different about this is that we've got the same thing. Energy is on our y-axis, and this is our reaction pathway, or you can think of it as time. And we're going to start at an energy, and we're going to end at a higher energy. So here our delta E is positive because we're ending at a higher energy than where we started, and that's called endothermic. So we're ending higher. All right, now enthalpy. It has the abbreviation H. That is the heat. So enthalpy is the heat that is released or absorbed from a system that is under constant pressure. So we can only measure enthalpy changes, and so we're always going to talk about enthalpy as delta H. And so delta H, just like everything that we have looked at with, with delta, delta is always final minus initial. So it's the enthalpy at the end of the system at the end of the reaction minus the initial. Okay, so again, this is delta H, and if you have a positive delta H, then we call that reaction endothermic, and if we have a negative, it's exothermic. All right, and again, here's just that picture again. We're saying that the sign of the enthalpy is negative, exothermic. Putting energy in, it's endothermic. Okay, so here now we're going to start adding some numbers. Here we have an exothermic reaction. How do we know that it is exothermic? Well, we know that it's exothermic because delta H is negative. That's the only way we know that it is exothermic. So delta H is negative. It's exothermic. That means that this system is giving off heat. So I like to think of it as putting an E over here. This would be a synthesis reaction if we were classifying them. And for every 2 moles of hydrogen that react with every mole of oxygen, generating 2 moles of water, there is 483 kilojoules of energy, and that energy is released. So you are releasing energy. And so that's why I put the E over here on the product side. That's what happens in an exothermic reaction. Okay, now an important point. Enthalpy is what we call an extensive property. It depends on how much you have. So this is a combustion reaction of methane. So remember, combustion produces CO2 and water, and oxygen is a reactant. Combustion reactions are exothermic, but in case you didn't know that, this negative delta H tells you that this reaction is exothermic. And so I still like to just add my E over here to remind me it was exothermic, energy was exiting the system, and 802 kilojoules of heat were given off with this reaction. Now, what if we doubled everything? What if we had 2 moles of methane and 4 moles of oxygen, giving us 2 CO2s and 4 waters? Well, because we have twice as much of everything, we are going to double our delta H, and so the delta H for this reaction would be negative 1604 kilojoules. So it depends on how much you have. So problem 1, how much heat is released when 4.5 grams of methane is burned under a constant pressure? All right, this is our reaction. Methane, when we have 1 mole of it, 802 kilojoules are produced. So let's go here, and we've got, let's see. Here we've got 4.5 grams of methane. Well, grams isn't going to help us at all, so here we go again. We need to convert this to moles, and a mole of methane is about 16 grams, and so that gives us 0.281 moles of methane. So the question is, how much heat is released when we have 0.281 moles of methane? We know when we have 1 mole of methane, 802 kilojoules are released. But we don't even have a whole mole. What we have is 0.281 moles. So here's what we have to do. We've got the conversion that we just did, 0.281 moles of methane. And we know from our balanced equation that when 1 mole was burned, 802 kilojoules were released. And so see how the moles cancel, and then we're left with kilojoules. I didn't put a negative sign in there because we're saying that the energy is released, and so that kind of takes care of it. And so it's 226 kilojoules will be released when 4.5 grams of the methane is burned. All right, so let's try another one. So in this reaction, we have ammonium nitrate, and it's a decomposition. Ammonium is +1, nitrate is -1, and it forms dinitrogen monoxide and water. And it looks like to balance it, we're going to need a 2 there. They said, again, it's a negative delta H. Not every delta H is negative, just so happens all these examples were negative. Had they been positive, it would have been an endothermic reaction. But anyway, this one is exothermic with E over here. And so let's go ahead. We have 2.5 grams of ammonium nitrate. And the molar mass of ammonium nitrate is about 80 grams. And so when we do this, 2.5 divided by 80, we come up with 0.0312 moles of ammonium nitrate. So we can see that there are 37 kilojoules released for 1 mole. How much is released for 0.0312 moles? And when you set this up, we're going to have 0.0312 moles. And we've got 37 kilojoules released for 1 mole. And so our answer is about a kilojoule. Okay, so we're adding a little bit of stoichiometry in with this thermochemistry. Now here's another important point, and this I think is kind of fun. What we have here is that last reaction, the combustion of methane. We've just flipped it around. So our products have become the reactants. So CO2 and water are our reactants, and methane and oxygen are now the products. So we have flipped the reaction. And so the magnitude of the delta H is the same, but now the enthalpy has the opposite sign for the reverse reaction. So here, with this reaction, it's a positive 802 kilojoules, meaning it's endothermic, and I would put my E over there. Okay, so that's just another important point that we're going to be using in our